Have you ever wondered how we measure something as impossibly small as the distance between two atoms in a molecule? It seems kind of crazy, right? Well, it turns out we can do it by making the molecule spin and then reading its unique signature, a kind of molecular barcode.
Okay, let's dive right in. What you're looking at here is the rotational spectrum for carbon monoxide. Now, at first glance, it just looks like a bunch of lines, doesn't it? A lot like a barcode you'd find on a product. But this molecular barcode is packed with information. Every single line and the space between them is a clue.
So what secrets are locked away in this pattern? Well, in this explainer, we're going to learn how to decipher this code. And by the end, you'll see exactly how we can go from these simple lines to figuring out the fundamental properties of the molecule that made them.
But first things first, not every molecule can actually create a barcode like this one. To even show up on the radar of a microwave spectrometer, a molecule has to meet two really crucial conditions.
Condition number one, the molecule has to be a gas. Think about it. We need it to be able to rotate totally freely without getting bumped and knocked around by its neighbors. If it were a liquid or a solid, the constant collisions would just kill that free rotation, smearing out all the beautiful, sharp lines that we need to see.
The second condition, and this one is super important, is that the molecule has to have a permanent dipole moment. Now that just means there's a permanent separation of positive and negative charge. It's this little imbalance that acts like a handle, you know? It lets the electric field of the microwave radiation grab onto the molecule and make it spin.
So, here's the bottom line. Molecules made of different atoms, like hydrogen chloride or carbon monoxide, have this dipole. We call them microwave active. But symmetrical molecules, like hydrogen or chlorine, where the charge is spread out perfectly evenly, they don't have that dipole handle. They are essentially invisible to microwaves, so we call them microwave inactive.
All right, so now that we know which molecules we can see, let's figure out how to understand their rotation. To make any sense of the spectrum, we need to simplify the molecule a bit and then apply the kind of strange rules of the quantum world.
You know, physicists and chemists love simple models, and the rigid rotator is a total classic. We just imagine our little diatomic molecule as a tiny dumbbell. You've got two atoms as the weights, and they're connected by a perfectly rigid massless rod. Now, of course, it's a simplification, but it works surprisingly well.
So a key property of this spinning dumbbell is its moment of inertia, which we symbolize with an I. Really, this is just a measure of how hard it is to get the molecule to rotate. And if you look at the formula, you can see it depends on the masses of the atoms and, most importantly, the distance between them. That R value, that's the bond length we're trying to find.
Now, here is the critical link. It's called the rotational constant, or B. This value is literally the bridge that connects the world we can see, the spectrum, to the invisible molecular world. We can measure B directly from the spacing of the lines on the spectrum, and as you can see in the formula, it's directly tied to that moment of inertia.
And this is where things get a little bit quantum. See, a molecule can't just spin at any random speed. Its rotational energy is quantized, which means it can only exist in specific, separate energy levels, kind of like the rungs of a ladder. The allowed energy for each rung is determined by that B constant we just talked about and a rotational quantum number J, which is just a simple way of labeling the energy level, 0, 1, 2, and so on.
And when it comes to jumping between these rungs, there is a very strict rule. A molecule that absorbs a microwave photon can only jump up one energy level at a time. It can't skip a rung. That's it. This is called the selection rule, and it's the absolute key to the pattern we see in the spectrum.
And this is how that simple rule creates our barcode. A jump from level 0 to 1, that gives us a line at 2B. From 1 to 2, a line at 4B. From 2 to 3, you get a line at 6B, and on and on. So what's the result? A series of lines where the spacing between any two of them is always the same, exactly 2B. That's our measurement.
So we've just decoded the spacing of the lines, which is a huge step. But if you look back at that carbon monoxide spectrum, you probably noticed the lines aren't all the same height. So what's that about? What determines their intensity?
The intensity of each line is all about population, basically how many molecules are in a specific energy level to begin with. And this is a tug-of-war between two opposing forces. On one side, you have the Boltzmann distribution, which is that graph on the left. It just says that molecules prefer to be lazy, they like lower energy states, so the population drops as energy goes up. But on the other hand, something called degeneracy means that there are simply more available slots or orientations for a molecule at higher energy levels. You combine those two effects and you get the curve on the right. The population goes up, hits a peak, and then falls off. And that peak, that's the most intense line in our spectrum.
Okay, we now have all the tools we need. We get the conditions, we have the model, we understand the rules, and we even know why the lines have different heights. So let's put it all together and see how we can take a real spectrum and do something incredible. Turn light into length.
It's really just a beautifully logical four-step recipe. First, you look at the spectrum and you measure the spacing between the lines to get the value of 2b. From there, it's just a simple chain of calculations. 2b gives us b. b, along with a few physical constants we already know, gives us the moment of inertia, I. And finally, using I and something called the reduced mass of the atoms, we can solve for the thing we've been after all along, the bond length, R.
And check this out. This technique is so sensitive, we can actually see the tiny effect of swapping an atom for one of its heavier isotopes. So if we look at a sample of carbon monoxide that has both carbon-12 and carbon-13 in it, we actually see two barcodes kind of overlapping. The heavier molecule is harder to spin, so it has a larger moment of inertia, which means a smaller B value, and that gives it a slightly more compressed spectrum. So cool.
So just how precise can we be? Well, for a molecule like hydrogen chloride, following these steps gives us a bond length of 1.2745 angstroms. I mean, that is a measurement down to a 10,000th of a nanometer, all figured out from how the molecule spins when you hit it with microwaves. It's just amazing.
So, why does all of this matter? Is this just some neat trick for physical chemistry students? No, not at all. This technique is not just an academic exercise. It has some seriously powerful real-world applications all over the place.
Its main use, like we've seen, is figuring out molecular structures with incredible precision. But astronomers use it too. They point radio telescopes at distant gas clouds and identify molecules based on their unique rotational barcodes. And right here at home, environmental scientists use it to keep an eye on atmospheric pollutants and greenhouse gases.
This brings us to a really interesting puzzle, and one that connects all this high-level science right back to your own kitchen. We said at the very beginning that this only works for gases. So why does a microwave oven, which obviously uses microwaves, heat up liquid water?
The answer is that your microwave oven is not a precision instrument. It doesn't care about neatly bumping a water molecule from one rotational level to the next. It just blasts them with a rapidly flipping electric field. The polar water molecules try desperately to keep up, wiggling and tumbling over each other, and all that bumping and jostling generates heat through pure molecular friction.
So, we've seen how decoding the spin of a molecule can tell us its size and its identity. It's an incredibly powerful tool. But rotation is just one way a molecule can move. And that leaves us with a final question. If this is what we can learn when a molecule spins, what can we find out when it starts to vibrate?